Now, to now we have, as I used to tell, we have talked about planets in our solar system, and then about the stars, mostly in our Milky Way, and how stars evolve into different phases. And then we talked about properties of our Milky Way, and also about galaxies and how galaxies are classified, what are their features, those kind of things, right? And last Monday, we talked a bit about Hubble law, which tells us that all these galaxies are moving away from us. And also we talked about what actually means by expansion of the universe, right? And also, so if I go back, some of the features of the galaxy is how the redshift is measured and how you can find the distances to these galaxies, and also how these galaxies looks like when you go back in time, especially for very early ages. Like if you look at a galaxy that is around 12 to 13 billion years away from us, we discussed that the shapes are completely different and they will not actually fit into this Hubble classification of system, which is Hubble tuning fork diagram, right, that you have done. And you have answered that question probably. And by the way, I have graded all of your that assignment, and you should see for some of you, I may have put some comments because some of you I have seen that not address the what question has asked, right? So you need to read the questions and answer according to that. And some of you did pretty well, and there are a few that I have seen that few information like is missing. So just check the comments if there is any. Right now, having all this information with us, and also we talked about the star formation, how stars are forming inside these galaxies, and how these star formation rates are different for different ages. And we actually talked about this particular diagram, which we called as Madhu diagram, right? And this graph right here, you have a graph that shows you with the redshift, increasing redshift, what will happen to the star formation rate. And we discussed that this the star formation rate has increased up to a certain level and start to decrease slightly. However, this part right here, you can see that kind of the data points are somewhat less when you go for this far redshift region, which means for the earlier times of the universe. The reason is, the technology is now currently developing, and these data will, more and more data will come in this region of the universe, right, in future with these modern telescopes, right? And then, so those are just few images to show you how these galaxies behave. And today, what I am going to discuss is, now what we know is stars are all grouped into galaxies, right? Now the question is, are the galaxies also grouped in some way? Right? So that will be the next question. So we know that we have stars and they are grouped into a galaxy, and we talked about galaxies. Now the next step is whether galaxies are grouped into a unit, right? Now, so you probably can think about this now, and what we are going to discuss today is about galaxy clusters. So those are the collection of galaxies, right? And galaxy clusters are normally considered as the one of the largest known structures in the universe, which are like gravitationally bound. Of course, there are superclusters, which is like collection of clusters. Right. Now, by studying the galaxies, we conclude that let's see how these galaxy clusters have emerged. So why we need to talk about the galaxy clusters, right? Now, this relates to interaction between galaxies. And if you look at these distant galaxies, right? Galaxies that were very far away, we conclude that the collisions and mergers of all galaxies play a crucial role in determining how galaxies acquire the shapes and sizes we see today, right? So what that means is, if you remember that we discussed last Monday, in early stages, you have the smaller size galaxies when you go for very high redshift universe. So that means uh, probably if you look at these 12 to 13, the galaxies, how they looks like when they are, 12 or 13 billion light years old, or 13 or 12 to 13 billion light years away from us, their size is smaller and their shapes seems to be different, right? Now, what has happened over the time is actually they have these smaller galaxies interact together to make these the large galaxies, such as the spiral and elliptical galaxies that we see in present universe, right? Now, these the collisions between galaxies is somewhat complex. It's one of the topics that astronomers are studying in modern days. So this the process of collision can take around hundreds of millions of years. So because of that, you cannot look at the sky and see like two galaxies. You cannot observe two galaxies are colliding each other, right? But you can see the evidence that they have collided or they are going to collide with each other, right? So that is the only way that we can observe those, right? And because of that, if you need to look at the complete picture of these collisions between galaxies, you have to simulate these on the computers, right? So that's what astronomers do most of the time if they want to look at the whole process of these collisions. So they have to, give these initial parameters and simulate those to see how these galaxies collide each other and what happens after that, right? What we know up to now is there are different types of collisions, but mainly if there are two galaxies of equal size involved in the collision, we call such an interaction as a merger. So it's kind of, rather than colliding each other, they will merge together, right, to become one galaxy, right? And the other type of type is actually if we have a small galaxy and a large galaxy. So it's obvious that what will happen is the large galaxy can attract the small one, and we used to tell that the small galaxies can be swallowed by the larger one, right? And this process is called galactic cannibalism, right? Now, what is important here is you need to identify what I mean from merger of two galaxies. And so that's basically when you have two equal sized galaxies involved in a collision, you will have a merger of two galaxies. And if you have two galaxies that, if you have one galaxy which is larger compared to the other one, then one galaxy will be get eaten by the other one or get swallowed by the larger one, right? So that is called galactic cannibalism. And if you look at the today's universe, galaxy mergers are very rare. Only about 5% of nearby galaxies are currently involved in interactions. And interactions were much more common billions of years ago, right? Now, so that is, you can think that in early universe, so they are very close by, and the environment is completely different. So you would expect that there are more interactions between galaxies, right? But as a result of that, in the present universe, what we can see is more mature galaxies. So more mature galaxies are created as a result of these different interactions between galaxies. And so galaxy interactions are actually sometimes observed through telescopes. And here are like two such interactions. The first one is called M82 and M83, the other two galaxies. So that you see here is a black and white image, and it's the same image right here as well. And this is also the same image. They are taken from different telescopes at different times. And here is another galaxy, two galaxies that interact together. And so since I do not have time to explain all this information, I have put all this caption here. You can just read through it and understand what has actually happened there, right? I just want to mention here, these are like examples of interaction between galaxies. And here is a computer simulation that two spiral galaxies merging and end up with a single elliptical galaxy, right? Now, these are the evidences that we have that we can think that these elliptical galaxies that we see today may be a result of interaction of two spiral galaxies, right? And on the other hand, if you remember that when you look at these spiral galaxies, they have more star-forming regions and active star formation that is going on. And elliptical galaxies are somewhat different. Mostly, they don't have active star formation. The stars that they have inside the galaxies are somewhat older, right? So that probably also an indication that elliptical galaxies are kind of older, so maybe they are created as a result of merger of two spiral galaxies, right? Now, I have mentioned here in the caption that this computer simulation starts with two spiral galaxies merging and ends with a single elliptical galaxy. The colors show the colors of stars in the system. What that means is, if you look at all these images, they are color coded based on the colors of stars, right? For example, when you go for this third image right here on the right hand side, you have more blue color right here. So that means you have more star formation in that particular situation, right? Now, the idea is when these two galaxies merge together, so they have a lot of interstellar matter, and when they interact together, that will help to burst the star formation, right? So which means you will have evidence for star formation during this collision of galaxies. Initially, you don't have such blue color here for the two galaxies. So when they start merging, and when the merging happens right here, because there is a condition, right? If you remember, for the star, in order for stars to form, there is a condition that needs to be satisfied, right? If you remember that we talk this as James mass under the topic of what triggers star formation, right? So that's what exactly happens here. So when that happens, you will see a burst of star formation. And after the collision is completed, that star formation kind of goes down, and then you will see an elliptical galaxy like this at the end. Right? Right, so here is an example of galactic cannibalism as well. And here are like, three galaxies colliding each other right here. And so just read through this caption that so I have put here. So you don't, I'm not going to explain the images that I have here. And here is a collision of galaxies that happen in a distant galaxy cluster. And what you can see here is the left side, this picture right here is a Hubble telescope image of a galaxy cluster, which is about 8 billion light years away from us. And So they have examined around like 81 galaxies right here inside the galaxy cluster. Out of those 81, then they have what they have identified is 13 of those 81 galaxies are the result of recent collisions of pair of galaxies, right? So what they have identified is around the 81 galaxies that they have checked in this galaxy cluster, 13 of those galaxies are actually collision of two galaxies, right? They have formed as a result of collision between two galaxies, right? Now there are 8 smaller images on this right hand side right here. So they are like close-ups of some of these colliding galaxies, right? So you can clearly see that there are two galaxies that comes close by, right? So that's why you have like two bright, dots right here in each galaxy. So they are in the process of collision. So those are the evidences that we have to tell that galaxies are interacting with each other, and this interaction process is more common in earlier universe than now. Right. Now, with this story about the collision between galaxies, let's look at how the galaxies are distributed in the space, right? So one thing that which is obvious is if we see that galaxies collide with each other, they must be fairly close together to have this kind of collision, right? Now, to estimate like how often these collisions occur and how they affect the evolution of the galaxies, what astronomers need to know is how these galaxies are distributed in the space over cosmic time. And that is important. No? So one thing that if we can know, we have results from that shows up from the simulation and also from this Hubble Space Telescope images that galaxies are colliding each other, and this process is more common in earlier universe, right? Now, in order to estimate how often these collisions occur, what we need to know is how galaxies are distributed in the space, right? Now, the main question that we have is whether these galaxies are isolated from one another, or do they congregate in groups? So that means they are collected as groups, right? And the other thing is how in general galaxies and their groups arranged in the cosmos, and are there as many in one direction of sky as in the other, for example. So that means we need to check if you look at a certain direction, whether you can see large number of galaxies compared to another direction, or whether you have kind of similar number of galaxies in each direction, right? Those are the things that astronomers and cosmologists try to observe to check how these galaxies are distributed in the space, right? Now, again, this astronomer called Edwin Hubble, who actually introduced the Hubble's law, found some answers to these questions. So what he did was a very we can talk about it in a very simple way, that he examined galaxies all over the sky, right? So what he did was actually in 1930, he photographs around 1,283 sample areas, and on each print he carefully counted the number of galaxy images. The technology that they have were not developed as what we have right now. So what he did was he photographed around this 1,283 sample areas, and then what he did was he carefully counted the number of galaxy images, right? So in each area, right? Now, what he found from his survey is that the number of galaxies visible in each area of the sky is about the same. So which means it doesn't matter which area you are looking at, roughly you can see same number of galaxies in each area. And this is one of the fundamental, concepts now in cosmology. And he also found that the number of galaxies increase with the faintness. That makes sense. And now what the idea is that at the end, what he decided is that the universe is both isotropic and homogeneous. And this is now we called as the cosmological principle. Now, isotropic means universe looks like the same in all directions, if we state it in very simple way, right? In every direction that you are looking at, the universe looks same. And the homogeneous means a large volume of space at any given redshift or distance is much like any other volume at that redshift, right? So it's like it's a story about direction and also how it looks like. So basically, so this is called cosmological principle. That is, the universe is isotropic and homogeneous. Once again, isotropic means it looks like same in all directions. As Hubble stated that from his photographs that you roughly see same number of galaxies in each and every direction. And the second one, homogeneous, means in a large volume of space at any given redshift or distance, it is much like any other volume at that particular redshift, right? And this is actually called as the cosmological principle, and you need to, it is very important that you understand and remember this because this is the fundamental principle in cosmology when we study cosmology, right? That is the idea. Right now, this is just an image of Edwin Hubble, who was working in his 100-inch telescope in Mount Wilson, California. And so the most of his findings actually based on his this telescope that he had. And also astronomers have measured the velocities and distances for hundreds of thousands of galaxies. And because of that, they were actually able to build up a meaningful picture of the large scale structure of the universe, right? And this is what we are going to discuss today, how in terms of the large scale, how the universe looks like. Locally, we know that we have the solar system and then we have stars in our galaxy like that, right? But what we are discussing here is if you look at the large scale, how the universe looks like, right? For that, astronomers have measured the velocities, basically the recessional velocities of large number of galaxies right now. So the rest of this section, what we are going to describe here is what we know about the distribution of galaxies, starting from the nearby galaxies, right? Now from the nearby, what we have is something called the local group, right? So Milky Way is a galaxy which is a member of this local group. But apart from the Milky Way, we have around 60 or so members in our local group. So the local group is actually not a galaxy cluster, it is called a galaxy group, right? Which means in terms of the size, it is smaller compared to galaxy clusters. However, it's still spread over about 3 million light years. And there are 3 large spiral galaxies in our own local group, that is our own galaxy and the Andromeda galaxy, and a galaxy called M33. So these are the 3 large spiral galaxies that we have in our local group. And we have around 2 intermediate elliptical galaxies, which means they are not as small as dwarf galaxies, but not as large as these 3 spiral galaxies. So basically you have 3 large spirals, 2 intermediate ellipticals, and many dwarf elliptical and irregular galaxies in our local group, right? And right here is kind of a diagram that shows you how our local group looks like And you can see that here is the central region, and this image is kind of an enlarged version of this central region of our own local group. And you can see our Milky Way galaxy is right at the center. And apart from that, there is an Andromeda galaxy, and you probably see the LMC and SMC, that is large Magellanic Cloud and a small Magellanic Cloud. And those are not visible in this picture, right? Because they are right at the central region with our own Milky Way. And these different colors represent different morphologies or different shapes according to Hubble classification. For example, the Andromeda galaxy M33, so these are spiral galaxies. So they are denoted from this yellow color, and blue is for elliptical galaxies, and the red color is, kind of, they represent irregular type galaxies. And this is just a, diagram that shows members of local group of galaxies, right? So this is this is the local group is the close by group of galaxies for us. However, if you look at for a large distances, these small groups are very hard to notice, right? But what you can see is in these large distances, there are large groups of galaxies, not like 50 or 60 members. They have, thousands of members together. And these type of structures are what we call as galaxy clusters, right? So that's what we call as galaxy clusters, right? And these galaxy clusters are not hard to spot even from many million light years away from us. And if time permits, I will show you some of the images that I took of these galaxy clusters. And these galaxy clusters are described either as poor galaxy clusters or rich galaxy clusters. And these two names are actually based on how many galaxies that they have, right? So there is no like hard and fast rule for that. If you see a relatively low number of galaxies in the cluster, we used to tell that it as a poor galaxy cluster, right? And if you have like 2,000, 3,000 galaxies that you can clearly see in the galaxy cluster, then we used to call that type of galaxy cluster as a rich galaxy cluster, right? So that's poor or rich. Those two words basically used depend on how many galaxies that each of these clusters have, right? So that's what I have mentioned here. Rich clusters have thousands or even 10,000 of galaxies. And then the poor ones means that it has a small number of galaxies. Now, the nearest moderately rich galaxy cluster is called Virgo cluster, right? You probably have heard this name. That is one of the close by galaxy clusters for us. The name is Virgo cluster, and it is not a very rich galaxy cluster, but we used to tell that as moderately rich galaxy cluster. Now, a good example of a larger, more rich galaxy cluster is the Coma cluster, right? So that is one of the popular galaxy clusters. And this cluster is centered on two giant ellipticals. So that means at the center of this galaxy cluster, you have two large elliptical galaxies, and each of these galaxies about 400 billions of suns each. So those are like huge galaxies. And actually for almost all of these galaxy clusters, if you look at these cluster images, there is one very bright elliptical galaxy at the center of all these galaxy clusters. And this galaxy, that particular galaxy kind of dominate, and see, I mean, you can very clearly see that it is very bright. And that particular galaxy is also called as a BCG galaxy, or a brightest cluster galaxy, right? So I have not mentioned it here, but that's some extra information. And And something that is, something that is that you can notice in all these galaxy clusters is also that you can see giant elliptical galaxies in the central region of a galaxy cluster, but few spiral galaxies at the central region. The spirals do exist generally on the outskirts of the cluster. Now, this is very interesting that when you take an image of a galaxy cluster, what you can observe is there are most of the spiral galaxies are around the central region of the galaxy cluster. Sorry, so I think I made a wrong statement here. Most of the elliptical galaxies are around the central region of the galaxy cluster, while most of the spiral galaxies are in the outer region or the outskirts. We used to tell that it's kind of close to the edge of the galaxy cluster. Right? So that is one of the very, very nice features that you can see that for each and every galaxy cluster, you can see this very clearly. Spirals are close to the center, so the ellipticals are close to the center, and the spirals are kind of in the outskirt region, right? So this is, so you can clearly see that now these are not, random features. So they are observed again and again, each and every galaxy cluster, you can see this, right? So I will probably show you using some of these images, probably maybe today or on the next day. Now here is the Virgo cluster, an image of the Virgo cluster. And you can again see that at the center, close to the center, you have this giant elliptical galaxy. And then you have other elliptical galaxies. Most of these elliptical galaxies are very close to the central region. And this probably, it's not clear, maybe this is a spiral galaxy. Like that, the most of the spiral galaxies goes into these outer regions in this around this area. This region is where you can see the spiral galaxies most of the time, if you have captured the whole galaxy cluster, right? And actually these images you cannot see it clearly because these are just JPEG images. But if you take an original image from a telescope, then you can see all these features very nicely by zooming it for different places. So I will show that to you, if not today, maybe on the next day. And here is the central region of the coma cluster. And this is combined visible light and infrared image. And these are color coded so that you will see the faint dwarf galaxies from the green color, right? And by the way, this image is a combination of images taken from this sky survey, which we called as Sloan Digital Sky Survey, or SDSS, and also the infrared. The same image is taken from the infrared telescope, from an infrared telescope, that is a Spitzer Space Telescope. These are kind of popular telescopes among astronomers due to the fact that their capabilities of imaging these galaxies and galaxy clusters. And Sloan Digital Sky Survey is, it's a multi-wavelength, huge survey that, look at the sky, different parts of the sky, and they have a huge database that even you can access. And practically, when you use, when you do some kind of research, you use to access these databases and get these galaxy cluster images, and which are very important to look at different features of galaxies and galaxy clusters. And right now, the next step is we know that we have galaxies and then galaxy clusters, which are group of galaxies. So when you have a large group of galaxies, we used to tell that it's a galaxy cluster. Now, the next step is we need to think now whether these clusters of galaxies also gather together. So that means we have galaxies, and then we know that galaxies collected together to make these galaxy clusters. Now let's see whether these galaxy clusters also gather together to form another unit, right? Now, to answer this question, we must be able to map large part of the universe in 3 dimensions. So to look at this, what we need to do is we have to look at a huge part of the universe, right? If not, you cannot see, larger structures. No, if you need to look at a larger structure, you have to observe a huge part of the universe in 3 dimensions to see how these galaxies are distributed. Now, as I mentioned earlier, the largest universe mapping project up to date is the Sloan Digital Sky Survey. So what they do is they map most part of the sky, right? So that at the end, once you have all the data, you can plot in the map and see how these galaxies and galaxy clusters are distributed on the universe, right? Now, interestingly, what we can observe is clusters of galaxies are not arranged uniformly throughout the universe, right? Instead, what we can see is you can see huge filamentary supercluster. So that means they are not randomly distributed everywhere. Galaxy clusters are actually not arranged uniformly each and every place, but they have arranged in a way that you will see huge filamentary superclusters. Basically, superclusters means when you see a large number of galaxy clusters collected in a certain place, then you tell that as supercluster. And details of some of these structures show that their masses are very huge, and sometimes 10,000 times more massive than the Milky Way galaxy itself. And you can think about the size of these structures. Right, now here is the map that the Sloan Digital Sky Survey made, and so this is from all the data up to now that Sloan Digital Sky Survey has taken. And I'm not sure whether they have finished the survey or not, but they have been conducting this survey since 2013 or 2014, and they have been operating these telescopes until very recent. But I'm not sure whether still it is going on or not. However, what we need to know here is this point at the center right here is where we are, right? It's like our own Milky Way, and then from there, these telescopes are looking at and observe our sky. And this scale right here is the redshift, right? So it kind of gives you an idea how far that we are looking at, right? Now, if you convert this value right here, 0.14, that is the redshift value. If you convert this value into a distance, you can do, I guess, using Hubble's law as well. You will see that we are actually looking at millions of light years away, right? Because I remember that I was looking at galaxy clusters up to this particular point. I will show those results to you. So still it was between 400 million light years to 2000 million light years away from us. So when you go for up to 0.14, that means you are looking at so far away, right? Even though not close to the beginning of the universe, but still it's a huge distance when you tell 0.14 redshift distance. And this is called hour angle. So I hope that you know what hour angle means, these numbers right here. And now everybody knows why these two regions are empty. You can see this is black and this is black, right? Anybody knows why? Why is that? Actually, that's because, so I probably have mentioned it here as well. Yes, the unmapped area is where our view of the universe is obstructed by the dust in our own galaxy, right? So you cannot, you cannot see through the disk of the universe, the Milky Way, because there are a lot of large number of huge amount of dust there, right? So even you have a telescope, you cannot look through that dust. So you are basically, there are two regions for both sides that you cannot do observations practically. So you will miss that part, right? So other than that, from the other data that they have made this map right here. And this is color coded as well, as I have mentioned here. The colors of galaxies indicates the ages of their stars, right? So that depends on the age of their stars, right? The redder colors showing that they have older stars, and if you have not that red, so that means they are blue stars, right? Or blue galaxies. So that means you have young stars, right? So that's how you understand it. And so you can see directly from this image, there are voids, so empty spaces here and there, and you have galaxy clusters. They are look like small filaments. So that's how they structured, right? So they are not randomly distributed, as you see. So this is what you can see when you get a huge sample of galaxy clusters and map it on a map like this, right? This is why we used to tell that clusters are found in huge filamentary superclusters, right? So they have a filamentary structure. They are not randomly distributed, right? And here is just for your information, the Sloan Digital Sky Survey Telescope is right here. And here is one of the famous astronomers, I guess, called Cron or something, is Richard Cron. He is, changing these some of the optical fibers there to change the instrument spectra and those kind of things. And what I need to show you is that how the technology has developed and how these people are working hard to get these things done. Right, so that's this. Let me show you. Yes. So what I need to talk with you at the same time is this box, the simulation results that we have, right? And this is a simulation starting from the beginning of the universe. Right here is what we call as the starting of the universe. That is why it tells here as the Big Bang. And after that, up to the present time, they have made this simulation to see how the universe looks like, right? Now, this is a simulation, computer simulation that they have done. The boxes show how filament and superclusters of galaxies grow over time. So at the universe, at the beginning, it's like this. And with the time, you can see that this filamentary structure grows with the time, right? And this structure is right here at the end. So this is what we see right now. And with few galaxies formed in the first 2 billion years. So for the first 2 billion years, only few galaxies have formed after the Big Bang, and then to the very clumsy string of galaxies which large operates today. So that is this structure right here. And so what is interesting here is now, this is the simulated image, simulated results, and you can see this structure right now from the simulation. And if you look at the result right here from the Sloan Digital Sky Survey, you can clearly see the similar type of structure right here, right? So that means these simulations that they have made and the observational results are agreed nicely. So that's why we can, confirmly tell that this is the structure of the universe on the present day, right? And so this is what actually, why science is very nice. They do simulations and predict that this should look like this. And then once you observe it, you can get the same results, right? So that confirms that our prediction and our way of thinking about the universe and this structure is correct, right? Right, so that's actually end up, so I have probably skipped some of these few images right here. So these are just images of few galaxy clusters for you to see how it looks like. And so since it's already 6:50, I'm not going to go for my next presentation, which is I will collect all this information which you have learned from these theories and try to show you on the next day based on my personal research, how these things are applied at different levels, right? The knowledge that you have here. But you will see that there are a lot of things that we have not learned as well. So I will quickly go through those just to show you how it works. And apart from that, I need to show you a few of these galaxy cluster images and as well. So at the starting point on the next day, in next Friday, I will show you some galaxy cluster images, and we can see how galaxies are actually distributed, and you will clearly see that elliptical galaxies are close to the center and spirals are, in the outer skirts, those kind of things, right? Now, before we stop, anybody have any questions up to here?